Greetings, differential equations scholars, and welcome to this second in our series of videos on section 7.2, the inverse Laplace transform. In this video, we'll do a little bit more practice finding inverse transforms, and we'll also discover a key result, which will become very important for helping us to use transforms to help solve initial value problems. We're going to begin with a couple of examples from your textbook. These are exercises 9 and 17 in section 7.2 of the ZIL text. The first problem let's take a look at is exercise 9, finding the inverse transform of 1 over 4s plus 1. Now we know that if we had 1 over s plus 1, we would recognize that immediately as being the transform of e to the minus t. But here we have 1 over 4s plus 1, so a little bit of algebra will be required. What we're going to do here is take that denominator and factor out a 4. So we're going to rewrite the denominator as 4 times s plus 1/4. Therefore, the fraction that we have is equivalent really to 1/4 times 1 over s plus 4. And now we're going to use that idea that we mentioned a minute ago. We know that the Laplace transform of an exponential yields a rational function very similar to the one that we have. We know that the Laplace transform of e to the at is 1 over s minus a. So therefore, it would follow that if we let a be minus 1/4, that e to the minus 1/4 t would be 1 over s minus negative a fourth, or 1 over s plus a fourth. So that means that this rational function here is the transform of e to the minus 1/4 t. So now by linearity, we have our solution. The Laplace transform of our original function by linearity is 1/4 of the inverse Laplace transform of 1 over 4s plus 1 by linearity is 1/4 of the inverse transform of 1 over s plus 1/4. So that's going to give us this result of 1/4 e to the minus 1/4 t. So algebra can be very useful. We'll see that again in exercise 17. In exercise 17, we want to find the inverse transform of 1 over s squared plus 3s. Now, certainly the denominator there can be factored into s times s plus 3. And remembering our example from our previous video, we're going to use the technique of partial fractions to break that up into the form a over s plus b over s plus 3 for suitable constants a and b. Let's find out what those have to be. Using partial fractions, if we multiply by s times s plus 3 on both sides of the equation that we have there, we would have that a times s plus 3 plus b times s has to necessarily equal 1, which we could also write as 0s plus 1. And then equating the coefficients, we know that a plus b, which is the coefficient of s, has to be 0. And we would know that 3a has to equal 1. Well, therefore, that tells us that b is equal to the negative of a, and that a is 1/3. So therefore, a is 1/3 and b is minus 1/3. And now we have our partial fractions decomposition. And we'll conclude that the inverse transform of our original expression is the inverse transform of 1/3 over s plus negative 1/3 over s plus 3. Now that first piece there, 1/3 over s, we know that the inverse transform of that is just the constant 1/3. The second piece we recognize as being a multiple, negative 1/3 over s plus 3. That is simply a multiple of 1 over s plus 3, and 1 over s plus 3 is the Laplace transform of e to the minus 3t. So the inverse transform of negative 1/3 over s plus 3 is negative 1/3 times e to the minus 3t. And there we have our solution. The inverse transform of our expression is 1/3 minus 1/3 times e to the minus 3t. There's a couple of additional examples for us of finding inverse transforms. As we're going to see, that skill is going to become incredibly useful for solving initial value problems shortly. We need to take a look at a key result here, though, that's going to become an important tool in our toolbox. And that is a theorem from your textbook. It's Theorem 7.2.2, dealing with the Laplace transform of a derivative of a function. The question we're going to ask here is, what would the Laplace transform of dy dt be? Suppose y is some as of yet unknown function, but it is one that has a Laplace transform, and that means it's exponentially bounded. What would its Laplace transform be? By the definition, we know that that Laplace transform would be the improper integral from 0 up to infinity of e to the minus st times dy dt. It would be that improper integral. We can do that improper integral using the technique of parts. Let's let u be e to the minus st, so that du is minus s e to the minus st dt. Let's let dv be our dy dt times dt piece. With that, its antiderivative would just be the function y. So then, invoking integration by parts, we'll have a first piece that's u times v, in other words, y of t times e to the minus st, and that's going to be evaluated at the upper limit with the upper limit going to infinity, and at the lower limit of 0, u times v, minus v du. Du is negative here, so minus minus the integral of v du essentially has a positive sign, and we'll take the s that's in the du and bring that out front, so that we get plus s times the integral of e to the minus sty dt, going between 0 and infinity. The interesting thing, though, is that we see that that integral that appears, the integral of v du, is also a Laplace transform, isn't it? Of course it is, and it's the Laplace transform of y, the antiderivative of the function whose Laplace transform we were looking for. So now evaluating these, what do we see? Well, this first piece, the u times v, when we evaluate it at the upper limit with b going to infinity, this piece is going to become 0. Why is that? Because we've said that the function y is going to be assumed to have a Laplace transform, and that means that it's exponentially bounded. That means that this piece here is guaranteed to go to 0 in the limit. What will it have at the lower limit of 0? Well, we'll have y of 0 times e to the 0, and that is just y of 0. So the first part of the integration by parts, the u times v, gives us 0 at the upper limit minus y of 0 at the lower limit. And we've just said a minute ago that we recognize that this integral is the Laplace transform of y. So this is s times the Laplace transform of y. And now we have a very, very useful result. What we found is that when you take the Laplace transform of the derivative of a function y, you get s times the Laplace transform of y itself minus the value of the function y evaluated at 0. Let's summarize that again. Suppose that we say that capital Y of S is the Laplace transform of little y of t. Using that familiar terminology and notation, what we've just shown is that the Laplace transform of the derivative of y is equal to S times the Laplace transform of y itself minus y evaluated at 0. In other words, we have found a way to express the Laplace transform of a first derivative using the Laplace transform of the function itself. That's a very powerful result. Indeed, it can be extended. If we wanted to use that to say find the Laplace transform of a second derivative, if we use that result, we could say that the Laplace transform of the second derivative of y, since the second derivative is the derivative of the derivative, we could use the same result. It would tell us that the Laplace transform of the derivative is S times the Laplace transform of the first derivative minus the first derivative evaluated at 0. That would be the result applying it to a second derivative, but then, of course, we can recursively take now the Laplace transform of the first derivative and replace that expression in. We said that we know the Laplace transform of the first derivative is S times the Laplace transform of the original function minus the original function evaluated at 0. Then multiplying out, we have this result. The Laplace transform of the second derivative would be S squared times the Laplace transform of the original function minus S times the original function evaluated at 0 minus the first derivative evaluated at 0. This would be the Laplace transform for the second derivative of a function. And we got that simply by repeatedly applying this formula that relates the Laplace transform of the derivative of a function to the Laplace transform of the function itself. A very useful result. And we're going to be using these results for the Laplace transforms of derivatives and leveraging them now to help solve initial value problems. Stay tuned for our next video in which we'll showcase the usage of these very helpful theorems.